as close to 6 o'clock as I'm willing to wait. My OCD's kicking in. We've got to get going with this. So thank you all for coming to our GCP meetup this month. This quick announcement, this may be the last one we host here. We've had an invitation from Google to use their offices going forward. So depending on when the timing works out, maybe the next talk, which will be on Flutter, from my friend Jared over there, will either be here or the Google offices. Either way, it will be on the site at some point in the next few months. We'll be migrating down the road to make use of the Google facilities. You won't have the view, but you will have better coffee, I'm sure.
For those of you that don't know, it's down off of June 3, so it's down there.
Yeah, not very fun. Okay, so having said that, next meeting's on Flutter. Hope you can make it for that one. I'd like to turn it over to Jim Brown. Jim is a data scientist on our team here at New Desert, and he's been working on some work around TensorFlow, which is actually going to be part of a roadshow demo that we're going to be putting on around the country later in the year. So you're going to get a first chance to see this. Jim, take it away.
Sounds good. Okay.
Oh, do you want to take over that?
Yeah, guys, get this.
All right, let me back it off. My screen's off.
Okay.
If you could share your screen and hang out.
Yeah, so,
No, I'm not seeing one here. Let's see.
oh, here we go. Entire screen. Share. Okay.
Oh, I think you lost it, Jim. You try joining again? Minor technical difficulties, sorry, everyone.
Guess while they're doing that, here's
Did I disconnect right now?
Looks like it, yeah. Do you need me to send you the invite again?
No, I think it's here.
Okay.
That's really I need to work. That's always one. It's like 100 of them.
Turn off Wi-Fi. Sorry about this. Okay, I'll connect first to, which one is this, Cafe? Yeah.
Cafe's working up there. Good.
Okay. Now the,
So if I have to ask, what are the advantages of being near the Google building versus being in this one, besides the fact that you guys use Google stuff a lot?
So the advantage of using the Google Office for meetings is they got a lot more space. So this, what we're all kind of trying to pack into a little area, won't happen. So that's the primary reason I'm supporting them. Plus, it's a little more central for most of you, I think, the airport area.
keeps dropping me, man.
Pardon? Untitled and TensorFlow? That sounds like a question for a data scientist and a cloud architect myself, so I'll hand that one over.
Matthew, I'm having some real trouble here. I can't get both
Excuse me.
working at the same time. So, you're not able to get to this.
Okay.
Right. And then when I come over here to do the hangout.
Yeah. Agnostic to but beyond that, sorry.
Now it.
Let's see what's going on. Hey, if we got to drop the live stream, that's fine.
Yeah.
We'll just do it here. fast, is it?
No, so. I don't know what speed I do.
It does. We'll drop the live stream and just do the presentation here. Here you go. So try sharing your screen.
This is where it popped last time.
Okay.
You okay?
What you know? Looking good, Jim.
It's lagging quite a bit. Okay. We'll try this. We may have to drop the live stream in order to get it to work. But thank you, everybody, for joining. My name's Jim, like Matthew said, and I'm a data scientist here at UDesik. And I'm really happy and excited to be able to present this topic to you. And what I'd like to do, I just have a couple of slides about machine learning in general, and then I'm going to dig into toxic comment classification. And that's a recent competition that was hosted by Kaggle. And that's in cooperation with Jigsaw and with Google. And it's a real-world NLP solution, and it's kind of at the forefront of research. And so I think this is a really good solution for me to kind of walk you through and show how the data science process works and how I approach these types of problems. It's really lagging. I don't think we're going to be able to keep going like this. Let me see if I can. All right, so here, when I'm presenting the screens, it's lagging and it's not really doing it. Can you see what I've got here on the screen, okay? Is everybody able to see it? Okay. Yeah, it knocked me off again.
That's okay, just keep going.
Okay. All right, so I found this weekend. So Wired just published this article, and it's the press is really enamored with machine learning, and they always call it amazing whenever it shows up. And especially their next favorite topic is probably chaos. And so as a mathematician, chaos means something very specific to me. And it's not randomness, it's actually, it evolves according to mathematical calculations. Okay, but it can go all over the place. And so this was a breakthrough that actually they were able to solve. And it simulates kind of this flame front that runs through this model. And so they've successfully been able to model chaos 8 times farther than they ever have before using machine learning. And what they did, these are 3 quotes from there, and I really like the quotes a lot, especially the third one over here on the side. It says, "This makes machine learning approach powerful. In many cases, the equations describing a chaotic system aren't known." So what they did is they actually used machine learning to solve a mathematical problem and to figure out what is that equation for the way that flame front propagates. And so that's fantastic. That is actually the same thing that we do in machine learning. So in supervised machine learning, we use training data to build a mathematical function that approximates all of the data that we have and gives us the correct answer. And so that's something like here you see, it's just the simplest case you can possibly have. It's y equals fx parameterized by w. And so both of those cases, x and w, are tensors. And x is our input, y is what we're trying to predict, and w is a tensor of weights. And tensors are just high-dimensional matrices. So what training does when we actually get into training is it makes tiny adjustments to the weights so that the function best describes the data. And that's really all it does. There's nothing magical about it. There's nothing, special. This is a mathematical operation. And so it's really important to keep in mind that our objective when we're doing machine learning is to predict an answer for something that we haven't seen before. It's not to go through the training data and to be able to predict that very well. That's not benefit to anyone, right? What we have to do is be able to predict the class of something that we've never seen before. And so what we call that is generalization of your model. Does it work on the training data, and does it work in real life? And that's what we try to maximize. Now, on the flip side of that is too much training. If we just train too much, what we end up doing is memorizing the inputs. So you can think of this like flashcards. If you just memorize flashcards and you memorize what the answer is, you haven't really learned anything. You just memorized some stuff, and it's totally useless in a real life situation. And so that's what we want to do, is constantly sort of balance between, have I learned enough to be a good approximation, and does this generalize enough, and have I not memorized the data too much? And so this is the Kaggle competition description. And so what they define a toxic comment as, and this is especially relevant today, because with the recent election we've had and all of the social media buzz around it, and people are fighting, they're using profanity at each other, it's a really hostile environment, and that causes people to leave these social conversations. So that's the problem that Google and Jigsaw are trying to solve. So they built this joint AI team to go after it. And so they kind of crowdsourced the solution and said, try and come up with a way to do this, given the training data, and see if you can figure out a better way to do it. And they paid $35,000 in prizes for this. This wrapped up, I think, just about a month ago. So what I'm going to show you is the architecture of one possible solution. It matches the winning solution, and it's a very good machine learning approximation, but it's not perfect. And so that's what I want to walk you through. So here's kind of the data science process. This is what I go through when I work on a problem like this. So the first thing is you get a hold of the training data, and you start trying to figure out what is the data? What does it have in there? What kind of distributions are there? What can I actually do with it? So then you also want to divide it up into training and evaluation. And this way you have a training set that you learn from, and then you have an evaluation set that you try to find out and gauge how well have I learned this task. And then we go into TensorFlow and Cloud ML to do the next set of tasks. And so I build a model using a custom estimator in TensorFlow. Then I train the model with the training set, and then I evaluate it with the evaluation set. And then I do hyperparameter tuning. And that is the most resource-intensive part of this. You run basically every combination of the hyperparameters in the model to try and tune and figure out which one works best. And so that works very, very well with Cloud ML, and I'll show you that in just a little bit. And then finally, once we're done with that, and once we've picked a model, we've tuned it, we know what parameters we're going to run with, then we train it one more time with every bit of data that we have. And then we put that into production, and that's the model that we actually use. So just a bit of a warning. This training data set contains horrific stuff. It's awful. It's basically the worst of humanity. And it's kind of sad to see. But if I pull up the tools and I show you data prep, some of this stuff is going to pop up on the screen. And I don't want to offend anyone, but we need to look at this in a forensic way. Okay? So these are the weaknesses of the training set. It a lot of times, if you think about the way that people insult each other, they insult them based on race, they insult them based on, gender, on, your sexual preference, all these kinds of topics. So these are things that are going to be very difficult for the model to deal with. And so exploring the data, you go right at these things to see what kind of bias is in the data and how does it deal with it. So this right here, let me expand this so you can see this. This is the prescriptive API that Jigsaw developed. And so this is their sample application that's published on the internet. So you can put in comments and it tests it against their model, and it will rate whatever you type as to how toxic it is. So I'm going to go straight into racial comments and comments about homosexuality, and we'll see how it rates it and what it's able to do. So the first one, I'll just put in that's 78% toxic, if you can see that. So Obama is a black man. There's nothing wrong with that. That's just stating a fact. But what they've done is this model has learned from the training data that race and being black is something that's toxic. And so it rates it that way. That's not right. That's something that we have to fight. Another one you can take a look at is just the concept of the word gay. That's 73% toxic. So these are things, when you think about machine learning and you say, we're coming up with a function, a mathematical function, right? There's not a lot of room in that for bias or for mistakes or stuff like that. It is what it is. So there's this big argument in machine learning that we just go where the training says, and there's an argument about bias and saying we should monitor our learning solutions to make sure that they're fair and that they don't learn these kinds of concepts. So that's one of the big things we have to do right away with this. Now, in exploring the data, I use Cloud Data Prep to do that. And here it is. Has anybody used this tool before? No? Okay, so this is still in beta. Okay, so what I really like about this is you point it to your data set. It pulls up the data set, and then it automatically, right across the top, it gives you the distributions of what's there. And so if you take a look at ID, this is a unique identifier. So everything is straight right across there. Same thing's true of the comment text. And then as I slide this over, you see toxic. This is what we're trying to predict out of this model. And it's labeled as 1 for toxic and 0 for it's not toxic. So we're doing binary classification. And so right away you can take a look at this, and you see that toxic with 0, 90% of my data is non-toxic. I only have 9.75% that is toxic. So I have a very small number of examples. So these classes are very imbalanced, and that causes a significant challenge to machine learning when we work with that. I only have about 15,000 examples. So when I start dividing it up into training and evaluation, I reduce the amount of information I can learn out of it. Another thing you have to pick up right away on this is if I just do a solution that says it's always non-toxic, it's 0, right? I am going to be right 90% of the time. So when you look at accuracy for your machine learning solution, you have to take that into account. I have to beat 90% in order to be able to learn anything out of this. So that's a goal that you have to kind of measure yourself against as you do this. Also, what's great about this is you'll see this little red right here. It tells me when there's a problem with the data. So I'm able to click on that. And then over here, it shows me here's a mistake in the training data. It's actually got a bunch of garbage in this one column. So it finds it, shows that to me. I'm able to click on it and delete those rows, get rid of it. It's also got one where there's missing data. So these are two things you always have to check. Is my data valid? And do I have any missing data? And what am I going to do about that? Another thing it does is when you look at the data, and I don't want to dig into it too much because it's awful, but there's things in there that you find like IP addresses. There's website URLs. There's all these types of information that I don't want the machine learning algorithm to use in coming up with how it decides if something is toxic or not. I don't want it to do something like, say, if your IP address starts with a 2, it's likely to be a toxic message, right? That has no relevance to it. So you have to build up these scripts. And the recipes over here on the side that ends up getting rid of this stuff. So the first one is getting rid of IP addresses. Then it's getting rid of URLs. And then I get rid of dates and times. And each time you do this, you're able to see on the left-hand side here, you're able to see what changes you're making to it and how it's being shifted and moved around. And that is fantastic. That saves, this is where you spend most of your time trying to get your data ready for it to be trained. And so by cleaning this all up, and I got my rules here, then I hit the run job, and then it runs a data flow job, and then I end up with my actual training data in cloud storage. And so that's the first part of this data science process. Now, as I'm doing this, I'm also trying to figure out what possible architectures can I apply to this. And in classification, there's bag of words. You look at that and you go, wow, I don't have, there's a lot of challenges to this. I don't think that model's going to work well. What other models could I bring to bear and use on that? So you're trying to build that as you're thinking about this and moving through it. So here's the architecture of the model. And I'll give you a quick look at this, and then I'll explain some of these different layers as well. So what I decided to do is to take a linear algebra approach at the bottom. So you read the model from the bottom up. So this is where the input comes in. And then this is 2 bidirectional GRU units. And then we do 2 dense layers at the top, and then we have our answer that comes out the top. Now, just take a sip here. All right, now has anybody heard about embedding layers or word vectorizations before? Is this new? Okay. So what we want to do, machine learning, and especially TensorFlow, it only knows numbers. Right, all of this, we're building a mathematical function that doesn't know anything about words. So what we need to do is convert the words into something that it can actually understand. And so the way we do that, the way I chose to do that in this case, is with these glove vectorizations. And let me expand this so you can see it. And this is really cool. So GLOVE was developed by Stanford University. They have a very, very good NLP group. And so what they did is they trained this, and the one I'm using is trained on 27 billion tokens out of Twitter. And they build up these vector spaces that they then share with the public. And it does some amazing things. So one of them is, and all I'm using is 50 dimensions. So here, what I'm going to do now is I'm just going to say, give me the vector for what the word awesome is. So there it is. There's the 50 numbers that represent the word awesome. Now, what I can also do which is really cool. I can say, what are the words that are close to that in the vector space? What's a near awesome? And it says it's unbelievable with an 86%. It's a number between 0 and 1 on the distance from awesome. So it's pretty close when you get an 86. It's got amazing, incredible, fantastic, marvelous. All of these things were learned by running this machine learning algorithm at Stanford. So my first tactic is, since I don't have a lot of training data, I'm going to leverage as much machine learning as I can from other places and pull that into my solution. So that's why we're doing that embedding layer at the bottom. Yes?
What's that listed or that array of numbers?
Yeah, so that is the vector representation of the word awesome. Okay, so what it does is it's representing it in a 50-dimensional vector space, and it says, this is awesome right here, and it points from the origin to that. And so what we're doing now is saying, what's in this vicinity? And so it's just coming back and it's saying, these are the 5 words that are closest to that. So what it's been able to do is to train on all of this data from Twitter, the 27 billion words that it's taken out of Twitter, including emoji and everything else, and it's able to put what's similar close to each other. Yes?
Are these matrices arranged in a graph, in a multidimensional graph?
They will be when I do training on it, but right now it's just a 50-dimensional vector space. So we're used to, like, when you look at a graph and you see X and Y, that's just 2 dimensions. We can picture 3, we can go X, Y, Z, but beyond that it's too hard to visualize. So all the same concepts hold, but this is 50 dimensions. And you can get 100 dimensions from Stanford, or you can get 300. And the more dimensions you have, the better it is in encoding the similarity between words. Now, I can also do something else that's absolutely amazing. You can do vector arithmetic on these words. So here what I'm going to do is I'm going to subtract man from king, and I'm going to add woman. So this is the standard example that they have. And when you run that, it says the answer is queen. So it also knows the relationships between different things. Now, you can also do that with cities. So you can say, now I want to take France, and I want to subtract Paris from that, and I want to add Munich. And the answer to that is Germany. So it's amazing the way it can do stuff like this. It can also, it's really, really good at analogies. So you can say, man is to woman as father is to mother. Okay. Now you can also do things like, you can evaluate, so these are things that have some kind of gender associated with it. Now what about things like jobs? So you can say, let's take chemist, and let's look at that. Let's say man is to woman as chemist is to biochemist. There's nothing gender related here at all, right? So chemist, biochemist, all these different kinds of things are all in the same area. So this has nothing specific about gender. But if you take a look at doctor, and we do the exact same thing, the answer is nurse. So now we have some gender bias in this, and that's carried on by the way we use language. So bias just sneaks its way in, and you have to be very, very careful about it all the time. So that's our embedding layer. And so the hope is, because we have such a small amount of training data, that this is going to bring some really high intelligence into the solution. Now the next layer, has anybody worked with GRUs before or know anything about them? LSTMs? Okay, this is signal processing. So the way these work, and it's a really, really simple concept. What we're going to think about is text as a signal. It has a sequence to it. It has a first word, a second word, a third word, and we move through that message like this, right? So what we're doing with these bidirectional layers with 13 cells, it means it's going to count. You pick a word, it's going to go 13 words before that, and it's going to go 13 words behind that, and that's the window it's going to consider when it actually looks at these words. Okay? And it's going to do that flowing through every comment. So it's got this big, wide thing that it goes by and it looks at. So what this does, this is fantastic. This actually knows the relationship between words. And so we put that on top of the embedding layer, and we start to get something that seems very, very intelligent. Now we have two layers there. The second layer does the exact same thing, but now instead of words, it deals with concepts. So it tries to learn, and it tries to figure out, what does race mean? What does the concept of homosexuality mean? It tries to do something with that, and we don't exactly know how that works, but it seems to do that. And then the next two layers, this is just pure classification. And so these two dense layers together is just how it figures out to say whether it's toxic or not. But all the really important stuff happens in these bottom three layers. Okay, does that make sense? Okay. Let me show you what that looks like in code. Okay, so this is VS Code, and this is our custom estimator.
I'm not sure.
Okay. Let me make it a little bit bigger. All right. So what we do, this is basically almost all boilerplate from the custom estimator examples that Google publishes on their website. What it does is the first part about loading up the embedding layer. That's what happens right here. It loads it from string, gets it into some TensorFlow variables, gets it ready to go. It's in lookup tables so that we can take a look at the word awesome. If it shows up, I turn it into the number 312, and then I go look in that space in the embedding matrix, and it goes, here's the 50 numbers that represent the word awesome. So that's what happens at the beginning. Then the next part is we actually build the model using those two GRU layers. And so what Google has done is they realize that almost everybody uses Keras to actually work with TensorFlow. So they've adopted that as their API, their high-level API. So instead of using the Keras libraries to do it, up at the very top, you import the TensorFlow versions of that. And so these are all the Keras labels that layers that I use. I pulled them in. I'm going to use the TensorFlow optimizer, and I'm going to use the TensorFlow loss functions. But that's the easy part. The hard part is trying to get your GRUs to work, and all of that is super simple with Keras. So you just have to use the latest version, 1.5, 1.6, whatever you can on Cloud ML, and that includes all of this. I won't spend a lot of time going through this because I know it's a little bit hard to see. But what we do is after we come out of that last dense layer, we have what are called logits, and these are log odds. So there's a formula to just convert that to what the actual probability is. So that's right here. So what it does is it just calculates what the probability is, whether it's 0, which means it's non-toxic, or 1, it is toxic, and then it calculates that and it makes the prediction. And then what we do is we just keep track of that in the loss. And what loss means, does anybody know what loss is? Loss is how close you are to the truth. So if a message is toxic, and I say it's a 0.8 probability that it's toxic, I'm off by 0.2. So that's how much loss I have in there. So we keep track of that, and what we're trying to do is instead of having everything be, I don't know, we're at 50% probability, what we're trying to do is push all of our predictions to the edges so that they're as close to 0 and as close to 1 as possible. And so when loss is a big number, it means we're in the middle. When loss is a small number, we're getting close to the edges. Okay? So that's our objective. That's how TensorFlow knows to make changes to the weights and get closer and closer to what we're trying to do. Okay, so all you have to do is tell TensorFlow what you're interested in, and that is the sigmoid cross entropy. Sigmoid is for 2, and it's great for just dealing with probabilities. Okay, then the other thing you do down here at the bottom, this is the next super important part. Right here, all we do is we say, hey, this is the optimizer. This is the piece that's going to adjust the weights. And the atom optimizer is a great optimizer. It works well in general cases. And all you have to do is tell it what your learning rate is. And the learning rate is when it figures out which way it's going to move, how far does it move? And you only want it to move a tiny bit. You don't want it to move too far. So that's it. That's all that TensorFlow does. Now the task, this is almost all boilerplate. I think I just changed like 2 or 3 words in here for my model, so I'm not even going to go through that. Okay, so now why use Cloud ML? I mean, there's lots of times you can just pull up, you can use your workstation, you can use Keras, and you can use TensorFlow as the backend for that, but why would you want to use Cloud ML? Well, that's the way I did this the first time when I worked on this competition. And so what I did is started the training, and right here you can see that it's estimating it's going to take it 1 hour and 17 minutes to finish 1 pass through the training data. Now, if I have to do 10 passes in my training path, this is going to take a good 10, 12 hours, right? That is a long time to wait. When I do this with Cloud ML, it's done in about 15 minutes. Now, I cannot stress enough how important this is when you do hyperparameter tuning. So, remember I said up here, I use 13 cells and 50 dimensions. Those are hyperparameters. How many cells work best? I don't know. 5, 6. Turns out it's 13 based on this training data. And the way it knows that is by running all those numbers through a training cycle. So if training takes 10 hours and I'm going to check 6 numbers, I've got 60 hours of training before I can make a decision. That's horrific. What I'm able to do, and then here I'll show you my jobs. Let me make this bigger. So here's a typical job that it runs. It ran a complete cycle, 4 passes through the training data, and it did it in 16 minutes and 40 seconds. And then I'm able to take that model and I'm able to evaluate it and look at it and see how did it do. Now, how are we on time? All right, so now all of this, as it's working and it's training, it stores all of this into cloud storage. So we're able to look at that, and we can take a look at my bucket, and we can see here's where everything is. I have to make this smaller. It's like looking through binoculars. Okay, so here's the data sets that I use for training, and then here's my job output. So out here it stores And this is actually really cool as well. It stores checkpoints of the model as it's working. So if your job fails while you're training, no big deal. Start it over again. It picks up where it left off. Just continues training from there. If you, for example, let's say I want to run it for an hour, and then I want to come back and I want to see how it's doing. I go, ooh, that's not quite good enough. I want to keep going with training. So I'm able to just pick up and go again. That's fantastic. So that's automatically built into it because I'm using the estimator model. That's why I went with a custom estimator. Now, they have predefined estimators that are much easier to use, but this is a really difficult problem, and so that's why I had to define it as a custom estimator. Okay, so now what you can do is take a look at using TensorBoard to see how's my training working. How am I able to judge that? So here's TensorBoard, and so let me just roll down here. Now I got to make it a little smaller. And then I'll make the graphs bigger when we look at them. Okay, so I did a really long training cycle, and this training cycle took about 2 hours to do, and I put 40,000 batches of training through it, which would have taken me almost a week to do on a high-performance workstation. And it did this really quickly, and it keeps track of what all the accuracy and information that it kept about it. So at the beginning, when it first started, it's not showing me the data point. Maybe if I do that. Okay, it's not giving me the pop-up, but what this is saying right there, you can kind of tell from the left, is that it's pretty close to 90%. If you remember, I said that's kind of like what a stupid, if I just said 0 for everything, I'd hit about 90%. That's where we started. It's just doing random guesses. Then after about 6,000 training cycles, we jump up to 96% accuracy. And we've also got this other metric down here. And this is area under the curve. And what this is doing is comparing the ratio of when I say a message is toxic, am I right or am I wrong? And taking a look at that. So if this is around 0.5, I know nothing. My model is useless. And so I start out with it right around 0.5. Even though I'm 90% accurate, this is useless. So then after a little bit of training, I'd get up to 84.75. That's a really good score. So our model is learning something, and it's learning something very well. Now we're also able to look at this while we're doing training. And so here's batch accuracy. So let's take a look at that. So I'm training in batches, and this is the number of batches. So 24,000, the number is bigger than that. It's 25,000 batches of training data went through. And so these vary all over the place because sometimes you'll get some that are easy to classify in a batch, sometimes you don't. So this is all over the place. So you kind of have to just sort of like say, well, the trend is going up, right? Even though it's going to bounce and move all around. No big deal. I'm getting better as I go along. But now something really bad can happen. And that's right here in this diagram. So see the blue line? It's like a hockey stick. It goes down and then it goes out flat. So what that means is that I'm learning, and I'm learning very well up until about 6,000. Then I flatten out. So from 6,000 on, I'm memorizing. I'm not really doing anything useful. So using this graph, I'm able to kind of see how training's going, and I can decide how big my batches should be and how much data I need to run and train on my model. This is incredibly helpful. Okay? So now I know how long and how much to train, and I'm getting good results out of it. Then the next step is you go back and you train for those 6,000 or 4,000 runs, whatever you pick, I want to train that on all the data. And then I have a model that I can work with. Okay, so let's take a look at that. Let's see how it worked. So that's right here. I'm going to ask it to classify a couple of statements. So I wanted to say Obama is a black man. We looked at that before. That the Jigsaw thought, their current model thought that was toxic. I'm going to do the word gay. We tried that. I'm also going to try homosexual. And then I'm going to try, what's close to that, but not quite. So we're going to look at the gay pride parade as today, right? That's something that's kind of similar to the other stuff, but it has important meaning in it. And then we're going to look at WTF, are you gay, right? That's obviously a toxic message, right? So let's run it. So what it does now is it's going out and it's pulling up that model. It's loading the estimator, and then this is just Python output and TensorFlow warnings that always come out. And it's running it right now, and in just a second, it's going to pop up and say what it is. Come on. There we go. Okay, so Obama is a black man, has a toxicity rating of less than 4%. So because we use this embedding and we use the GRUs, it's able to understand that that concept is not toxic, right? Even though we don't have that case in the training data. So we're generalizing very well on race. We're doing great there. The word gay is still 63% toxic. We got a lot of work to do there. Now the next one, let's see, what was the homosexual? The word homosexual is only 19%. So the concept of being homosexual or being gay, it knows that's not toxic. But the specific word gay is used so many times in the training examples that it's putting too much weight on that. And then the parade comment, that's only 13%. That's clearly a non-toxic message, and it knows that. But the last one is 84% toxic. So we've done a really good job at learning something from the training data, but it's not perfect. So then the question becomes, how do we do any better than this? And that's a really difficult problem. NLP is super difficult. And just to give you an example.
Question.
Sure.
On the last example, do you think there is some bias because of the usage of WTF?
Yes. It definitely, all of the profanity is in the same area in the vector space. So even if it hasn't been trained on something like that, if it's in that same space, it will know that that's profanity. So that's one of the great things about the embedding layer, that it's able to take similar words that are close to it and use that. But it's also, it knows that if you're talking about gay and you're talking about profanity at the same time, that's probably a toxic message, and it probably puts a ton of weight on that, right? But that's not always the case. There are lots of times where that may not be the case, and that's one of the things that Jigsaw pointed out, is that maybe there's websites that profanity is allowed, and that's not what makes it toxic. So there's different scenarios, and this is the research that got the entire group working on this problem. It is a very, very difficult problem. And so here's a kind of a famous quote. We value all Americans, including lesbian, gay, bisexual, and transgender ones. This is something Obama actually said. That is a 9% toxicity rating, even though I used all of those words. Now, with just 2 letters, I come over here and I change that to EX. We've gone from something that is actually non-toxic to something that's extremely toxic, but they only rated that at 7%. They memorized that phrase, and their model is recording that, reporting on that. Now, mine, both versions of these are toxic, and it's not able to deal with that. Yes?
Was the original phrase in the training data?
Not in my data, but this is one of the things you try to do when you're doing machine learning, is to go out and find public sources of information. President's speeches are very, very popular training items. So you pull that stuff in. You pull in Twitter data. You pull in Wiki Talk data is what the toxic messages are coming from.
We
So
had memorized it, so
yes.
so that's what I was wondering is if it had already been trained on.
Yeah, so this is Jigsaw's model. This one isn't mine. This is just an example of how sticky this topic is. It is really difficult, and this is why a lot of techniques with languages don't work as well. And so this is at the forefront of like research and where we're going in this field and trying to figure this stuff out. Okay, so that's about it on the topics that I wanted to present. So, questions? Anything you'd like me to talk about some more, or comments?
Question. So the example of the sentence having been memorized, is that a concept of overfitting? Is that kind of what that is, or is it just memorization?
Yeah, it's too much training with that set of data. It causes problems like that. So kind of the follow-on thing is, well, what can I do in order to make this better, right? What's sort of the next step? So the first reaction most people have to that is, I'm going to go over here and I'm going to play with my architecture. I'm going to try and come up with another architecture, and I'm going to test that and see if that works any better. You're wasting your time. Okay? What you do with machine learning is, I use my experience to pick this model, right? This is because this one should perform well at this task. So I either do two things. I spend time getting more data, or I work on the model some more and try and fine tune it. But I don't want to switch models or go to something else, because I still have the same amount of data going into it. So the amount of effort versus reward is going to be almost pointless. Right? It's a very, very important concept in machine learning. There is no best algorithm for doing machine learning. You pick one that's good in this scenario and you use it, and you're going to be fine with it. No matter how this architecture works, you're going to do well. But if I can go out, like let's say the example is, I need to teach it more about the word gay. And when is that toxic and when is it not toxic? So I have to go out and I have to find examples using that word in a non-toxic way, and I have to add that to my training set. That will give me a massive improvement, whereas messing with my architecture may only give me 0.5% improvement. Okay?
How much data did you, I know data prep strips them out, I'm sure, but how much data did you start out with current analysis?
It's like 159,000. There's actually, let's see. Yeah, so there's 143,848 non-toxic messages in the training set. There's 15,278 that are toxic. That's not a lot of data, right? So, yes.
So those were short messages, like tweets?
These are actually from the Wiki Talk pages. So this is, they are partnering with Jigsaw and with Google to try and solve this problem. And I had no idea there was this much nastiness on Wikipedia and the way they argue and fight with each other.
So I'm wondering how it would work on, let's say, a forum where some of the replies are going to be multiple paragraphs, and there might be something inflammatory you know, in the middle or in the end, but it wouldn't be the whole,
Yeah.
whole post.
That's a great point, and that's exactly why I chose GRUs to do that. Because what it's going to do is it's going to consider words in that window, and it's going to make its decision based on that. And so the words that are around it, well, it will be able to learn the concept part of it, that second layer. Let me pull that up. So this layer right here, if you get longer messages, it has an opportunity to learn more concepts from that message. So it'll kick in more and it'll contribute more. So you may say the exact same thing that it might evaluate as a toxic statement, but used in context in a larger paragraph, it goes, that's not toxic.
Right, well, I'm thinking of posts where someone maybe replies and says, you're an idiot, and blah, 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 blah. And the blah, blah, blah is fine, it's just they were really rude initially, or...
Yeah.
So how would it rank something? I mean, is it gonna weigh the toxic part higher than the rest, or?
I would have to dig into the layer and the weights to actually figure that out, but I can speculate about that because all those weights and how it rates that is something that it learns from the training data. So it tries to find out what's the best solution, considering all the comments, what's the best solution I can get to that will generalize well. So this first layer should fire off and say, this is a toxic message, right? And then the second one should come back with some more context about it and have more input, and then maybe it will or will not flag it. It's hard to know exactly what it would do. Yeah.
So how good would this be for interpreting quote-unquote coded messages? So the example of this, like in China, it's very hard to criticize, so people come up with very, very clever ways. So for example, a comment that's actually extremely toxic is, Winnie the Pooh is eating too much honey. But that's first, that doesn't sound like a bad statement, but that's actually an extremely excruciating criticism towards maybe your boss or maybe your, some local politician. So how would this detect some kind of coded language where you're not exactly bringing up the keyword, but you're using coded language to kind of have a low blow on someone?
That's a great example. So the first way is the embedding layer. So we use 27 billion tokens to train it. And that includes Chinese, it includes several other languages, it includes emoji, and it's all this other stuff in it. So it should know what you just said. It should be able to have some representation of that. And then in the training data, if that example is in there and it's flagged as toxic, it has a chance to learn from it. If it's never seen something like that, it may have a small chance of figuring it out. But
how does one flag this toxic? You have to actually decide and say this is.
Yes, so these are the examples you provide as training data. So we're doing supervised machine learning. So I have 15,000 examples that say these are toxic messages. So the one you used, if that were in my training data, it would certainly be aware of it and how to deal with it.
I guess what I was saying is, unless you actually knew the code and like the inside talk, it would be very hard without any manual verification and knowledge of the inside to be able to do that.
That's exactly right.
How you would be able to get around that problem?
There's not a lot you can do in that case. That's a hole in your training data if you miss that.
Like, also an example of this is, for example, you could say, for example, a term that was used in the 90s to describe people who may have been disadvantaged, they called them welfare queens. But unless you knew what the association meant, you would say, oh, well, those people ought to go. But until you realize that that was code for, it would be very hard to say that was a toxic comment or not.
Right.
Unless, I guess that's my point is, I think, how would someone...
So in another example that I actually played with to try and figure this out is Dick Cheney's daughter is a lesbian, right? So we combine all kinds of words that could be used in different ways. It's just a statement of fact, and how did it do figuring that out? it's sort of like in the middle. It doesn't know what to do, but it doesn't flag it as that's a toxic statement. So it is still able to get some hidden meaning out of things simply by using this architecture and the embedding. And that's one of the amazing aspects of this. So what happened before? Let me give you a little history here. Before 2014, everything was done, like spam detection, all that was done by counting the number of words in a message and saying, how many times did this appear? And then that's how you would decide if something was spam or not. In 2014, they came up with this word-to-vec structure, and all of the breakthroughs in machine learning and NLP pretty much are using this technique. So this is the kind of like every major breakthrough they're making right now is based on this. So it's a great technique to know and have.
This model, can you switch to like an unsupervised mode?
You could, but in unsupervised, you would be looking for patterns in it. And so it would be difficult to do a classification problem in an unsupervised way, but you can certainly use this vector space to do that. Yes?
Using the model that you create, you're trying to find, say, a toxic comment.
I didn't hear the first part.
Using the model you created, did you actually create a toxic comment?
Yeah, that's actually, this is a really interesting concept that they had. The winners of the competition looked at this and they said, I don't have very much data. I need to get more data. So what they did is they went out and they translated all the toxic comments into French. They used like the Google API, the Translate API to do that. They converted into French, Italian, Chinese, Spanish, and then they converted it back to English. And so then they had now a whole lot more data worded in different ways that they could train on and work with. So what you try to do is, and the same thing, if we were working with images, we would try to slightly rotate the images, zoom the images, do something to it so that we end up with different cases for it to look at. A lot of great questions.
So I'm going to jump in at this point, I know we're about 7 o'clock.
Okay.
Which is about our time. I want to say it looks like we had technical difficulties. So we have an audio recording of today's, but no visuals. So Jim and I, over the next couple of days, will work to put this slide deck and any other content that we can up on the site so you can go find it and correlate it with what we heard today. Please join me in thanking Jim. He did this on very short notice for me because he had someone else. And there is still some pizza. Please eat it. I don't want to take it home. And Jim, you'll be here for another 10 minutes or so to answer any more questions you might have. Thank you, everyone.